Thank you very much for giving me the opportunity to talk in this very interesting Einstein Toolkit summer school. Unfortunately, my talk is possibly not going to be as interesting, physically speaking, as others we've already seen, as I'm going to be talking mainly about a rather minor but important step in one of our long-term projects we have. So let's get into it. From a numerical simulation point of view, it is especially interesting to include future null infinity, also called future light-like infinity in Scribe+, in our numerical domain. So this can be done with usual standard Cauchy slices, as they don't reach Scribe+ unless we use extrapolation. But if we put them together with characteristic foliations, we can use Cauchy characteristic matching or extraction to be able to reach future null infinity. But in order to avoid the place with this foliations are joined, we can also use hyperboloidal slices, which are spacelike and smooth everywhere to reach future null infinity. And as they automatically give more resolution to a central part, they are a bit more efficient. So the relevance of including future null infinity is because it's only at infinity that we can determine lower properties of the spacetimes, and especially gravitational wave emission is only unambiguously defined at null infinity. One way of trying to get there is via Penrose's conformal compactification, where instead of working with the physical metric that will diverge at Scribe+, we multiply it by a conformal factor that goes to 0 at the appropriate rate, so that we obtain a finite rescaled metric that we can use everywhere. Now, the catch is that the Einstein equations in terms of this rescaled metric are going to have formally singular terms that we have to make sure cancel appropriately in order to be able to numerically simulate them. Now, there exists a spherically symmetric code of the Einstein equations on hyperboloidal slices. And here I'm showing the way the scalar field behaves when coupled to them. So our initial pulse is given here at time equals 0. It splits into two parts. One of them moves towards the right and leaves the domain through Scribe, which is located at r equals 1. The other part is reflected at the origin, and then afterwards also leaves through Scribe+. And here we can see the signal that it would leave at future null infinity. Another example of the simulations we can perform is a collapse. So the scalar field here in purple is going to create a black hole. And the interesting part is that we can see the whole slice from the origin up to now the trumpet, up to future null infinity at r equals 1. And here, by the way, the black vertical curve is the location of the apparent horizon that has formed. Now, we would like to go beyond and go up to 3D, but this is not completely straightforward. So, oops, sorry. So instead of going forward with the Einstein equations, we're going to first consider simpler models, such as the wave equation. So we're going to try the wave equation in a three-dimensional code. This has been done before. There exists an Einstein Toolkit thorn called Llama Wave Hyperboloidal, developed by Michael Jasulek. Sorry if I mispronounce his name. That solves the conformal invariant scalar field as a first order and flux conservative form. So I would I plan to implement, I'm working on implementing the non-conformal invariant wave equation, which is given here. Because as the Einstein equations are also not conformally invariant, we expect that they will, they also present this type of formally diverging terms. So this is closer to what we want to do with the Einstein equations. As well, I would tend to use second order in space system. And ideally, I would like to not have to match a hyperboloidal slice to a Cauchy one in the interior, as is done in Llama with hyperboloidal, where that's the way they deal with the Kerr background in Kerr-Schild coordinates. So far, I have only been able to evolve on Minkowski background, although we plan to move on to Schwarzschild soon. And by default, I tend to use spherical coordinates instead of the Cartesian ones, but let's see how that goes. Now, so far, I can only show you these preliminary results. This is not done with the Einstein Toolkit, but with NRPy. And I have to say I'm quite happy because once I just got the equations coded in, it worked pretty much out of the box. I'm still working on a few things, but it's very promising already. So what you see here, let's start on the left. So this from the center to the boundaries of the plot, you basically have the radial coordinate, and so the circumference around it is actually the location of frictional infinity, square plus, and these are for a fixed value of the theta angle, is in spherical coordinates, and so basically, and the phi angle is the one that actually makes it look like this. I'm just going to play it. It's not going to look especially interesting. Initial data, it just gets propagated away, and in the end we just obtain Minkowski spacetime empty, nothing there. And here on the right we have the same pretty much equivalent simulation with initial data, which is not spherically symmetric, so it has a bit of a richer dynamics, but it's pretty much the same thing. And in the end we just get empty Minkowski. So for the quality of the simulations, I've performed some convergence tests. This one is a bit cheating because this is actually just a simulation in axis symmetry, because the one I perform in 3D do not look so good yet, but I'm working on it. So here we use second order finite differences, and here we need to recover the second order quite well, so in time. But still more work needs to be done. Now, unfortunately, the implementation as part of the Einstein Toolkit as a thorn is still ongoing. It's going slower than I had planned, so I cannot really show you any results from that yet. I'm basically following what was done previously in this Lambda wave hyperboloidal. The important bit that it includes is that it has an outer spherical shell, and that's what we need because in 3D, scribe plus is going to be a sphere, and that's important. And for the interior, I still have to see whether I try to use spherical coordinates or Cartesian ones. What we plan as future steps, be it in NRPy or in the Einstein Toolkit, is to first substitute the background for something a bit more interesting, such as Schwarzschild or Kerr trumpet geometry. And I mention a trumpet geometry because it allows us to go inside of the horizon, and that's quite interesting. And then I would also implement the good but ugly model, which is is semi-linear and thus better mimics the behavior of the Einstein equation, especially at the asymptotic limit towards pi plus, and before trying the full non-linear Einstein equations in 3D, we would attempt a linearized version. So that's everything. Thank you very much for your attention, and I'll be happy to answer any questions that you may have.